The bacteria that cause strep throat will grow at a rate of about 2.3% per minute. To the nearest whole minute, how long will it take for these bacteria to double in number? So this is you've got a compound growth thing there. You get a choice, really. You can either assume that this compound or this increase happens in increments, as in at the end of each minute 2.3% is added to the growth, and it happens right then and only then. It's like a discrete model effectively. So after minute 1 it'll increase by 2.3%, minute 2 it'll do it again. Your other approach is to use a continuous model, as in an exponential model. Now it depends where you're looking, but I would say you will always get full credit, unless you're specifically told to do otherwise. You will always get full credit for using the exponential model. You may not always get full credit for using a discrete growth model. And if you think about it, it's more realistic that growth's going to be taking place continually if it's a biological process after all. So we are going to use something like this. So A0, or A as a function of t, equals A0 e to the RT. So we're going to see this is an exponential model. What that means, the amount of bacteria at any given time equals the original amount times e to the RT. Now t is obviously your time. R is it's your percentage increase rate as a decimal. So R is going to be 2.3% as a decimal. So you get 2.3 and you divide it by 100. So divide it by 10, 0.23, it's going to be 0.023. When you divide by 100, it's very important that your R is the percentage as a decimal. Do not just put it in as a percentage. It is a bit confusing because if this was, say, a compound interest formula, you would put it in as a whole number, but you do need to remember this. For this you don't. T is just going to be the time in minutes, and it's going to be what we're going to find anyway. Now you've got this AT and A0. We don't know what they are technically, but we know that we're looking for the time when the bacteria are doubling in number. So you're looking, well, when does AT equal to A0? That's what situation we're looking for. So if you have an A at any time t equals 2A0, so we know that AT over A0 equals 2. And if we know that AT over A0 equals 2, then we should be able to make this formula look a lot easier. So if we put everything in that we know, so AT equals A0 e to the 0.023t, then if we just divide both sides by A0, well, that would be e to the 0.023t equals AT, the amount of bacteria at any given time t, over the starting amount, as in amount of bacteria at time 0, when at the initial beginning of everything, of the growth. So we know that AT over A0 is 2 because we're looking for the time when the actual amount is double the initial amount. So we can now substitute in this is just 2. So we have 2 equals e to the 0.023t. So now we have a nice exponential equation, and we want to make t the subject, so we want to be taking logs off both sides, so we can use that third law on it. ln2 equals ln e to the 0.023t. Remember, I don't mind if you go straight from here to ln2 equals 0.023t, that's fine, but I'm not going to. Also, as far as the bases go, I'm taking natural logs here. I would always opt for a natural log if I wasn't sure anyway. But if you look at this, this is about the natural, this is about e anyway, so we definitely want to be taking a natural log. So now we use the third law, it would say ln2 equals 0.023t lne. lne is 1 because it's the power you raise e to get e. e to the power 1 is e. So ln2 equals 0.023t. So now all we need to do is divide by 0.023. ln2 over 0.023 equals t. And remember, t will be the time in minutes. We go to our calculators. That's not right. Try again. ln2 over 0.023 equals 30.13. So t, we've been asked for it to the nearest minute, so that must just be 30 minutes. In fact, I will write down the decimal, 30.1368. It's a good thing to see as an examiner. The t equals 30 minutes.